Welcome to my class on correlation and regression. In this video, I'm going to be taking you through the concept of correlation and the concept of regression. Quickly, let's differentiate between these two concepts and also explain what they mean. So, there are two concepts that make the topic. One is correlation and the other is regression. Now, these two concepts appear similar, but there is a slight difference between the two concepts. So what does correlation mean? If there are two variables, x and y, two variables in particular, x and y, the correlation between x and y simply talks about the relationship between x and y in relation to the strength between x and y, the relationship between x and y, or the weakness of the relationship between x and y. So it is under correlation we answer the question, is there a relationship between x and y? And if there is, how strong is that relationship? How weak is that relationship? To do this in correlation, we use what is called the correlation coefficient. And I'm going to be discussing that subsequently in this video. So, correlation is a concept in statistics that talks about the relationship between x and y, two variables in relation to their strength or weakness. However, if we seek to model the relationship between x and y, we would be discussing the concept of regression. Okay? So, correlation talks about the relationship between x and y, two variables in relation to the strength of the relationship or the weakness of the relationship using a correlation coefficient. Whereas regression talks about the modeling of the relationship between x and y. Modeling in this case simply means using an equation, which we call the model, of course, to determine how x relates with y or how y relates with x. So please hold on to those two concepts. I'll be putting them quickly on the board, the meaning of both of them, which in other words tells you the difference. So let's start with this. So I'm going to start with saying correlation is a concept in statistics as a field, of course, that describes the relationship between variables in relation to the strength or weakness, in relation to the strength or weakness of such relationship using what we call a correlation, using a correlation coefficient. Okay, so this quickly in summary describes the concept of correlation. Now, for regression, I would say regression is also a concept in statistics. Regression is a concept, of course, in statistics that models the relationship between variables. Now, having said that about the difference between these two concepts based on the description I've given you, of course, that of correlation and regression, let's now focus on what I'll be calling categories or types of data. So, now, this is, of course, very important in our discussions on correlation and regression. Why? Now, we shall be considering the first type of data we shall be considering being univariate data. The second type we shall be considering will be bivariate data. And this would help us narrow ourselves down to what should be discussed in this particular lecture. The third type of data we'll be considering will be multivariate data. Okay? So the question now is, what is a univariate data? Now, what we call a univariate data is a data that describes an item in relation to one object in question, or you could even call it a variable in question. Okay? Now, what does this mean? Take a look at a simple example that I'm going to be giving you in this video. So, let's assume that there are boys, which I will describe as my item, and there is a variable height, which I will describe as my object. So, if you want to study the item boy in relation to this variable, just one variable height, the data you obtain can be classified as being univariate, because in this case, you are considering an item in relation to one variable alone. So let's assume that there are 5 boys in question: boy 1, boy 2, boy 3, 4, and 5. For each of these boys, you'll be taking values of their heights. So if the height of this boy comes out as h1, the height of the second will come out as h2, h3, h4, h5. These will be the values of this random variable height coming from measurements taken on each of the boys. So in this case, we say this data you have obtained in relation to this item from this variable alone constitutes what we call a univariate data. So simply put, a univariate data is a data that describes an item in relation to one object or variable in question. Now comes the bivariate data. A bivariate data, on the other hand, is a data that describes an item in relation to two variables or objects. Okay? So, in this case, like the previous case, let's consider the item again, boys. So, if boys would constitute your item, you can now consider variable 1 as height and variable 2 as weight. Okay? So, in this case, the item remains boys, so I'm considering 1, 2, 3, 4, 5 boys. But this time around, I have height, a first variable, which constitutes a measure on these boys. So this will give me h1, h2, h3, h4, h5 as the height measurements taken on the 5 boys. And this will give me w1, w2, w3, w4, and w5 taken as the weight measurements on these boys. When you carry out measures on two variables in relation to one item, this kind of data, the height and weight considered in relation to boys being the only item, would make for what is called a bivariate data. So, our focus in this particular lecture will not be on the correlation of univariate data. The correlation of univariate data will be taken care of in courses like time series, where you will be dealing with autocorrelation, because you are now considering the correlation between a particular set of data with previous values or future values of that same set of data. In bivariate data being the focus in our study, we'll be considering the relationship between two variables taken as measurements on a particular item. So if we so desire to find the relationship between height, and weight taken on boys, then we will be dealing with the correlation of bivariate data, which is the focus of this particular study. Now, let's come over to multivariate data. A multivariate data is a data that describes an item in relation to more than two variables. So, in the first instance on univariate data, we considered one item being boys in relation to one variable being height. In the second instance, we considered one item, still boys, in relation to two variables, height and weight. What if we decide to consider boys as our item in relation to heights, in relation to weights, and in relation to, let's say, mass or whatsoever measurement you can take on these boys. So if there are 5 boys, 1, 2, 3, 4, 5, like we took previously, you end up having measurements of weight for the 5 boys, measurements of height for the 5 boys, and measurements of mass for the 5 boys. That is just an illustration. Now, these 3 variables, which will be measurements, which will give you measurements on the boys being the item, would constitute a multivariate data, because in this case, we are looking beyond 2 variables in relation to an item. So let's quickly recap. 1 variable, 1 item, univariate data. 2 variables, 1 item, bivariate data, which is the focus of this study. And then more than 2 variables, 1 item constitute what we call a multivariate data. So please take note, when you see us finding the correlation between 2 variables alone in relation to 1 item, know that the focus of this study was simply on a bivariate data. That being said, let's move on to the next thing. Now let's consider what we call a scatter diagram. A scatter diagram. Simply put, a scatter diagram is a graph of the bivariate data. A scatter diagram is the graph of the bivariate data. So now that we know that the bivariate data simply describes one item in relation to 2 variables, it means that if there is a variable y whose relationship we consider in relation to another variable x, then a plot of y against x will give us points within the Cartesian plane. These points plotted within the Cartesian plane constitute what we call a scatter diagram. Okay? Now, why is it a graph of a bivariate data? It is simply because x and y are measurements taken on one item, and when you plot the values of y against x or x against y, as it were, it will give you a graph of this nature. Now, the next thing I shall be discussing are the categories of this graph. In what forms can you have the scatter diagram? And I'm going to simply tell you quickly that the scatter diagram can be used to show what type of correlation you are discussing. Meaning that you could be discussing a linear correlation case, or you could be describing a non-linear correlation case. We are going to be using the scatter diagram quickly to show the difference between these two. So let's see how that is done. Now, let's start with the linear scatter diagram. So I'm going to put here linear scatter diagrams. How do the linear scatter diagrams appear? To start with, I'm going to show you that there are 3 cases under the linear scatter diagram. So let's put this as y against x, as y against x, as y against x. Okay? So these are 3 different two-dimensional rectangular Cartesian plane. I'm going to put here now a plot. Let's see the first instance. If it so happens that when you plot the values of y against x, it gives you points in the Cartesian plane that are scattered about such that it is impossible or near impossible to put a straight line across these points, showing the direction of movement or plot of the points, then this kind of scatter diagram, which I'm going to call figure A, will be a case of zero correlation. So if it is not clear as to what direction the plots put on the two-dimensional rectangular Cartesian is going, then it means that it is simply describing a case of zero correlation. It tells you that there is a possibility of no relationship between y, the values of y, and x. What it means is y cannot be used to tell what the values of x will be, and x cannot be used to tell what the values of y will be. More or less, there is almost no relationship between the values of y and x. In correlation, our question would usually be, is an increase in x going to provoke an increase in y, or an increase in y going to provoke an increase in x? Will a drop in y values also determine a drop or provoke a drop in the x values? Now, clearly looking at this type of plot, you will notice that you cannot tell if y is increasing as x is increasing or y is decreasing as x is increasing. You cannot tell for that case. For that instance, we describe this scenario as a zero correlation case. Now, let's move over to the next case. In the next case, if it so happens that the plotted points move in a direction such as this, such that if you want to put a line across a set of points from amongst these, it will show you that the direction is upward. Okay? The direction of movement is upward for all the points. In this instance, notice that an increase in x is obviously showing an increase in y, and an increase in y is also showing that there is an increase in x. This kind of correlation, which I'm going to call figure B, tells you that we have a positive correlation. So if it so happens that an increase in x leads to an increase in y, then that kind of correlation, as determined by the scatter diagram, is a positive correlation. What if the values of x or the values of y decrease as the values of x increase? In which case, you have plots appearing in this manner, such that if you choose to put a line across them, the line will go in this manner. For this kind of plots, as shown or determined by the linear scatter diagram, take note that this kind of correlation, which I'm going to call figure C, will determine a negative correlation. Why is it negative, guys? It is negative because the values of y are decreasing as the values of x are increasing. So, why are they all linear cases? They are linear cases because they can be described only by straight lines, and they are also positive, zero, or negative for the reasons I have provided you. In this case, there is apparently no correlation between the variables because the points are scattered all over such that one cannot put a line showing the direction of movement of the points. In this case here, looking at all the plots, you will notice that if one is to draw a line across the point, it will show this direction that as y increases, x is also increasing. Looking at the third diagram, it is negative because as x increases, y values are decreasing. So simply put, there are three cases for the linear scatter diagram: figure A, figure B, and figure C. Let's now go to the non-linear case. So, how would the scatter diagram appear for the non-linear case? You could have scatter diagrams appearing in this manner if the relationship between x and y, that's the bivariate data, is non-linear. So how would we look at a scatter diagram and tell that the relationship is there but is non-linear? If it so happens that the points you plot seem to follow a curve-like movement, the movement about a curve. So if you have plots not following a straight line but appearing like this, such that if you were to put a curve about them, you may have something like this. In this case, we would say our correlation is non-linear. I'm going to call this figure D. Our relationship is non-linear, but it is positive. Okay? It is positive. So this particular case is a case of positive non-linear correlation. Take note of the fact that the shape, the curve, is convex. Okay? Now, if it so happens otherwise that the points are concave, following a curve-like pattern, but concave, that is the plotted points, such that if you were to put a line across them, you would have a figure like this, which I'm going to call figure E. Then you would say the correlation is negative. In this case, the plotted points follow a concave structure. So linear scatter diagrams could appear in three forms. Nonlinear scatter diagrams could appear in either of these forms. So our focus will be in this course on linear correlation. As such, we will dwell on linear scatter diagrams. Okay, let's proceed to the next thing. So now let's move over to the next thing I want to discuss, which is fitting a regression line or model. Okay, fitting a regression model. Now, the regression model we shall be looking at in this case will be called a simple linear regression. And I'm going to explain that quickly. Now, why is it a simple linear regression? It is simple because it is linear because the highest power of our variables in the model we shall be developing is 1. Okay? For the response variable and also for the dependent variable and the parameters also. More so, it is simple because the relationship we intend to model involves just two variables alone, x and y. Remember, our focus is on a bivariate data. So, when we say fit a regression model, what do we actually mean? It simply means describe an equation that connects the variable, the response variable, say y, with the independent variable, say x. Okay? So, if there are two variables y and x, in which case, for this instance, I'm taking this as my response and I'm taking this as my independent variable, then a simple linear regression model will be of the form y equals, I'm going to put this, y equals beta naught plus beta 1 x1. If we are discussing just one variable, I'm going to leave it as x plus an error term. So precisely, let's put this as our simple linear equation. Now, this is our simple linear model or equation, but it is not the fitted model. Now, when we say fit a regression model, in this case, we are going to be using a method called least squares technique. Okay? So, to fit a regression model in this instance, we shall be using the least squares technique. And in this case, fitting a regression model simply means needing a model that minimizes or eradicates the error term. And that would end up giving us an equation such as this, where beta naught will be an estimate, beta naught cap will be an estimate of beta naught, beta 1 cap will be an estimate of beta 1, and the error term, an estimate of the error term gives 0 and it vanishes. So this is the equation we want when we tell you that we want you to fit a regression model to a bivariate data. Now, the question is, how do we go about getting this particular equation? That is what we shall be doing immediately. Let's see how that is done. Let's fit the regression model I told you earlier. That is, let's fit this. Beta naught cap plus beta 1 cap x. Okay? So this is the model we want to fit, and to fit this model implies that we must get the exact values or expressions in this case for beta naught cap and beta 1 cap. So how do we go about doing that? Now we will start from the general model we had previously, the one that contains the error term. Notice that in this model, this form of the model, there is the error, and in the fitted model, there is no error. So that involves, to get this particular model, involves getting the exact expressions for beta naught cap and beta 1 cap. Take note that beta 1 cap and beta naught cap are estimates of these two parameters. So the first step, which is my step 1, will be to obtain the square of this error term. So I'm going to obtain the square of this error term, or more or less, let's call our first step sum of squares. Okay, we are going to obtain the sum of squares. So the first thing I'm going to do, let's call this equation 1 in particular. From equation 1, I'm going to make error the subject of formula. So I'm going to have this. If you make error the subject of formula, epsilon I being your error would now be yi minus beta naught minus beta 1 xi. So that's more or less a first procedure I'm going to take under step 1, which involves getting the sum of squares. Now the next step will be to obtain the square of the error terms, in which case squaring this side, the left hand side, would imply squaring everything you have here. So that's like a second procedure under step 1. In step 3, I'm now going to take summation of both sides. Okay? So I'm going to take summation of both sides from I equals 1 to n, and that would also imply taking the summation of the right hand side from I equals 1 to n. So that's what I'm going to do, and this all squared. Okay, so let's now call this particular part, let's call this S. Let's call that S, and that will now imply that to end step 1, S will be equal to summation from I equals 1 to n of yi minus beta naught minus beta 1 xi all squared. And this concludes step 1. Let's move over to step 2. Now that we have obtained S to be the sum of squares of errors, what now do we do? The next thing we are going to do will be to apply the classical derivative technique, where we shall be differentiating this S here. We shall be differentiating the sum of squares of errors with respect to beta naught and beta 1, equating them on each occasion to 0. Okay, so that's what we are going to be doing next. So I'm going to say differentiating, let's call this equation 2. So I'm going to say differentiating equation 2 with respect to beta naught gives the following. So let's see what it gives. So I'm going to use my partial derivative to differentiate S, the sum of squares of errors with respect to beta naught. And that means differentiating this sum from I equals 1 to n, yi minus beta naught minus beta 1 xi all squared with respect to beta naught is the same thing as taking the sum of their derivatives. So this comes out and derivative goes in with respect to beta naught of yi minus beta naught minus beta 1 xi all squared. So at this point, this is what you are going to have. This does not mean that the actual derivative has been done. So the actual differentiation has been done, sorry. Now, the one thing we are going to do here is, looking at it, this is partial derivative, and we are differentiating with respect to beta naught. This implies that anything that is not beta naught or has beta, that does not have beta naught as attached to it, becomes 0 in differentiation because it will be taken to be a constant. Now, let's do that. So my sum comes out, summation from I equals 1 to n it will be preferable for us to start, since this is a function of a function case, differentiating with respect to the mother function outside. So I'll do that first of all to get 2 in bracket yi minus beta naught minus beta 1 xi when differentiating the outer function. And that will be 2 minus 1, which of course is 1. So let's now go into the bracket to differentiate the child function yi minus beta naught minus beta 1 xi. If you differentiate this, this will be seen as a constant, as I mentioned earlier. This will be seen as minus 1. When you differentiate beta naught minus beta naught with respect to beta naught, you get minus 1. And this will be 0 because there is no beta naught there. So this ends up being minus 1. And on simplification further, you would have from I equals 1 to n minus 2 yi, or if you want to simplify at once, you would end up having minus 2 yi. When minus 1 multiplies 2 times yi, then when minus 1 multiplies 2, it gives you minus 2 times this minus beta naught gives you plus 2 beta naught. This gives you plus 2 beta 1 xi. So we can go further by doing the next thing. So going from our last result, the next thing we are going to do, you could further expand, and that will give you minus 2 coming out as a constant, and the summation takes on yi. Okay, so using the summation now to open up the bracket, you end up having the summation goes into the second term. This gives you 2 beta naught, because you are summing both of them being constant n times, you are going to have n, 2n, preferably 2n beta naught, and the last will be 2 coming out, beta 1 coming out as a constant, summation from I equals 1 to n, 2 beta 1, summation I equals 1 to n xi. So that's what you are going to have, okay, as the s, the beta naught. Now, for, the next thing you are going to do will be to equate this to 0. So I'm going to say equating the s, the beta naught, our final result to 0. Then we are going to have the following. We are going to have minus 2 summation from I equals 1 to n yi plus 2n beta naught plus 2 beta 1 summation I equals 1 to n xi being equal to 0. Okay? Now I'm going to make anything containing y the subject of formula. So in this case, I'm going to have minus 2 summation I equals 1 to n yi, my subject of formula, and this would all go the other way, becoming minus 2n beta naught minus 2 beta 1 summation I equals 1 to n xi. Okay, so when I do that, that's what I'm going to have. Then of course I can divide through by minus 2. When you divide through by minus 2, you end up having a final result as summation from I equals 1 to n yi equals n beta naught plus beta 1 summation from I equals 1 to n xi. This is the result you're going to get. Let's call this equation 3. So hold on to this and see the next step. So now that we've established that result for equation 3, let's go back to differentiating. Remember that equation 3 was obtained by differentiating equation 2 with respect to beta naught. Now we are going to differentiate equation 2 with respect to beta 1 and then equate to 0 also. So let's do that. I'm going to differentiate this with respect to beta 1, okay? And doing that similarly would mean differentiating this sum on the left hand side, yes. So you end up having differentiation of this with respect to beta 1 yi minus beta naught minus beta 1 xi all squared. Okay, and that will mean differentiation of a sum is equal to the sum of the derivative. So in that case, I'm going to bring out the sum and take the derivative in with respect to beta 1 yi minus beta naught minus beta 1 xi. Okay, all squared. Now this is at this point what I have. Now, if you start differentiating this time around with respect to beta 1, my summation, of course, comes out. You are going to end up having differentiating yi with respect to beta 1. You don't start with that. Differentiate the outer function first. I'm going to differentiate the outer function, which gives me 2 in bracket yi minus beta naught minus beta 1 xi. In case you don't know, I'm using chain rule of differentiation. Now that we've differentiated the outer function by using 2 to multiply the coefficient and then subtracting from 1, we are going into the bracket to deal with the child function, yi minus beta naught minus beta 1 xi. And this time around, differentiating it with respect to beta 1. So differentiating yi with respect to beta 1 gives 0 because it is seen as a constant. Differentiating this with respect to beta 1 is seen as a constant, so it gives you 0. But differentiating this with respect to beta 1 makes xi appear as a coefficient, and that will give you your result as minus xi. Okay, so you end up having your result as minus xi because you are, in this case, differentiating with respect to beta 1. Now, once that is done, it means we can now summarize our result as summation from I equals 1 to n minus xi multiplies 2 and multiplies yi to give you, in bracket, 2xi minus 2xi yi minus xi multiplies 2 and then multiplies this to give 2 beta naught xi minus xi multiplies 2 and then multiplies this to give you plus 2 beta 1 xi all squared. So this is the result you are going to get when you expand with this summation. 2 comes out, minus 2 comes out, and you end up having summation from I equals 1 to n xi yi. Plus 2 comes out, you end up having plus 2 beta naught summation from I equals 1 to n and xi here. Then when you have this particular term treated with the summation, you end up having 2 beta 1 summation from I equals 1 to n xi all squared. So this will be the result you get for differentiating this with respect to beta 1. And we are going to be equating this result to 0 and then simplifying. So let's do that quickly. Now we are going to equate this to 0, and that will mean 2 minus 2 summation from I equals 1 to n xi yi plus 2 beta naught summation I equals 1 to n xi plus 2 beta 1 summation I equals 1 to n xi all squared equals 0. So if you make the term that contains y the subject of formula, you are going to end up having minus 2 from I equals 1 to n xi yi equals minus 2 beta naught summation I equals 1 to n xi minus 2 beta 1 summation I equals 1 to n xi all squared. Now, dividing through by minus 2 gives, if we divide through by minus 2, you end up having summation from I equals 1 to n xi yi equals beta naught summation from I equals 1 to n xi plus beta 1 summation I equals 1 to n xi squared. That's what we are going to have. I'm going to call this equation 4. Okay, so let's call that equation 4. The next step, which is my step 3, will be to obtain the parameters. And we are going to be doing this, obtaining the parameters, beta naught and beta 1. Estimates of the parameters, please. We are going to obtain estimates of the parameters. So you could put that. Now, to obtain the estimates of the parameters means solving equation 4 and equation 3 simultaneously. Let's do that. So, to obtain the estimates of the parameters beta naught and beta 1, we are going to solve this system of equation simultaneously. For us to do that, I'm going to start with eliminating beta naught. The essence of eliminating beta naught is to get beta 1. So, to eliminate beta naught, I'm going to multiply equation 3 by the coefficient of beta naught in equation 4. I'm going to multiply equation 3 by the coefficient of, I'm going to multiply equation 4 by the coefficient of beta naught in equation 3. So it means that I'm going to use summation xi I'm going to use summation xi to multiply equation 3, and I'm going to use n to multiply equation 4. Okay? So doing that means I'm going to get the following result. So this will become summation from I equals 1 to n xi times summation from I equals 1 to n yi. And that will be equal to n beta naught summation from I equals 1 to n xi plus beta 1 summation from I equals 1 to n xi all squared. So I'm going to call this equation 5. Now, using n to multiply this gives us n summation from I equals 1 to n xi yi. Okay? Using this to multiply this, using n to multiply this gives us a balance of this. Okay? Then using n to multiply this gives n beta 1 summation from I equals 1 to n xi all squared. And that is the result we're going to get. I'm going to call this equation 6. Now, subtracting equation 5 from equation 6 gives, so subtracting equation 5 from equation 6 means this minus this, which gives you 0, and this minus this. So when you subtract this from this, which is this minus this, you end up having n summation from I equals 1 to n xi yi equals minus summation from I equals 1 to n xi summation I equals 1 to n yi, and this will be equal to this minus this is 0, so we don't account for this, but this minus this will give you n beta 1 summation from I equals 1 to n xi all squared, okay, minus beta 1, I'm going to bring this result down here, beta 1 summation from I equals 1 to n xi all squared. So that is what we are going to have. From this particular result, I'm going to make beta 1 the subject of formula. And as soon as you make beta 1 your subject of formula, you have to put a cap on it to show that that is the estimate. Okay? So let's do that quickly to round up this result and then obtain beta naught. Now, making beta 1 the subject of formula, we are going to have beta 1 cap, and that will mean on this other side, you are going to have beta 1 cap into bracket n summation I equals 1 to n xi all squared minus summation from I equals 1 to n xi all squared. Okay? And that will be equal to all we have here, n summation from I equals 1 to n xi yi minus summation from I equals 1 to n xi summation from I equals 1 to n yi. So this now gives us beta cap 1 as beta cap equals n summation from I equals 1 to n xiyi minus summation I equals 1 to n xi summation I equals 1 to n yi all over what you have standing beside beta 1, which is n summation I equals 1 to n xi squared minus in bracket summation from I equals 1 to n xi all squared. So this will be the expression with which one can obtain beta 1 cap, being the estimate of beta 1. Now, the next thing to ask ourselves is, how then do we obtain beta naught? So to obtain beta naught, all we have to do is to recall this equation. Yi equals beta naught cap plus beta 1 cap xi. Okay? Assuming that this is the fitted model. Now, if this is the fitted model, one can now actually do this. Take summation from I equals 1 to n of yi on the left-hand side, and this would imply taking summation from I equals 1 to n of beta naught, which will give you beta naught cap, and this, which would mean taking summation of from I equals 1 to n of beta 1 cap xi. Of course, beta naught cap is a constant, so summing a constant n time will give you n beta naught cap. Okay? And summing this product of a constant and xi, the variable there, would mean the constant comes out beta 1 cap summation from I equals 1 to n xi. And this will give you summation yi from I equals 1 to n. Now, if you quickly divide both sides of this last expression by n, if you divide this by n, implying that you divide this sum by n, you end up having beta naught cap plus beta 1 cap x bar. That is the mean, and this will give you y bar. So for you to now obtain beta naught cap, all you have to do is to make it the subject of formula from this last expression. That being said, let us now go to the product moment coefficient. Now, from our last results, we had obtained beta 1 cap to be this and y bar to be equal to this, from which one can obtain beta naught cap if you know the value of beta 1 cap, x bar, and y bar. So what we are going to be doing now is to go over to product moment correlation coefficient. So correlation coefficients, like I mentioned earlier in this video, correlation coefficients are used to tell the strength or weakness of the relationship existing between variables, in particular for a bivariate data, two variables. Okay, so what other name is there for a product moment correlation coefficient? If you don't want to call it product moment correlation coefficient, you can call it Pearson's correlation coefficient. Okay, so let's start with obtaining the formula for the Pearson's correlation coefficient, otherwise called product moment correlation coefficient. So what we are going to do is R, which represents the sample correlation coefficient, is the square root of beta 1 cap times beta 1 cap prime. Now, you might be wondering, where is beta 1 cap prime coming from? Take note, we regressed y on x, hence giving us y equals beta naught cap plus beta 1 cap xi. This was our fitted model. This was when we regressed yi on xi. And in this case, when you regress yi on xi, the coefficient of xi is beta 1 cap. If, however, we so choose to regress xi on yi, we'll end up having beta naught cap prime as a parameter and beta 1 cap prime as the parameter, in this case being coefficient of yi. So this is where it is coming from. And if you take the product of those two coefficients and take the square root, you end up having what we call the product moment correlation coefficient. So let's quickly obtain that. So what I'm going to do next, having told you that, will be to take the square root of what we obtained earlier on. Now, regressing y on x will give us beta 1 cap as this. N summation from I equals 1 to n xi yi minus summation xi from I equals 1 to n summation from I equals 1 to n yi. Okay, I'm going to put this in bracket and extend this. Okay, all over n summation from I equals 1 to n xi squared minus summation from I equals 1 to n xi. This should have been, please, let's correct this, all squared. So this would have been all squared. So please take note of that correction I made. Now, this would multiply. This is a case of beta 1 cap when you regress y on x. Now, since we are multiplying it with beta 1 cap prime, then it means the numerator will still remain the same for beta 1 cap prime. So I'm going to still have this summation xi summation yi from I equals 1 to n, I equals 1 to n. Okay, but this time around, since I'm regressing x on y, I'll end up having n summation from I equals 1 to n. So let's put this in a square bracket. I'm going to have this yi all squared from I equals 1 to n minus summation from I equals 1 to n yi all squared. So now take note that the numerator can multiply itself to give you the square of one of them. Taking the square root of the numerator ends up giving you just one of them, meaning that for the numerator, we'll end up having summation from I equals 1 to n xi yi minus summation from I equals 1 to n xi summation from I equals 1 to n yi all over. Now taking the square root of this product gives us n summation from I equals 1 to n xi squared. I'm going to break this here so that you can actually see clearly what is actually going on. So this will be from I equals 1 to n xi all squared. Similarly, I'm going to put here summation from I equals 1 to n times n yi squared minus summation from I equals 1 to n yi all squared. Now, what have we just obtained? What we have just obtained, if you follow through on what I've just done, is called the product moment correlation coefficient, otherwise called the Pearson's correlation coefficient. Let's move on to the rank correlation coefficient. Rank correlation coefficient is another type of correlation coefficient, and we shall be putting up the rank correlation coefficient formula, which is R equals 1 minus 6 summation I equals 1 to n di squared all over n into bracket n squared minus 1. We shall be using this and the product moment correlation formula to be solving a problem. So I'm going to be showing you in this video how to use both of them to get the correlation coefficient. Now, the next thing I want to do is to tell you about the property of the correlation coefficient. So whether by rank correlation or by product moment correlation coefficient, I'm going to be showing you the properties of the correlation coefficient R. However, please take note of the fact that if you don't want to call it rank correlation coefficient, you can call it Spearman's correlation coefficient. Some people would often call it Spearman's rank correlation coefficient. So please take note, rank correlation coefficient is also known as Spearman's correlation coefficient. That being said, let's take the properties, some properties of R. Some properties of the correlation coefficient. Number one, please take note that R must lie between -1 and 1. So if you obtain your correlation coefficient R must lie between -1 and 1, meaning that your correlation coefficient can never be greater than 1. You cannot have a correlation coefficient of 2 or 1.9 or 1.2 or anything above 1. Neither can you have a correlation coefficient lesser than -1. It must lie between -1 and 1. Okay? Now, 2, when R equals 1, we say you have a perfect positive correlation. So if the relationship between x and y for a bivariate data is 1 as told by the correlation coefficient, then it means that that relationship is perfect and positive. If R, however, is equal to -1, we say it is perfect negative correlation. Okay? So these are extreme cases. If R equals 0, we say no correlation exists. Okay? No correlation exists between the two variables x and y. Now, please take note. This gives rise to another property you can think of or look at. The closer R is to 0, the closer R is to 0 tells you how weak the correlation is, or almost non-existent, okay, between x and y. So if the correlation between x and y for a bivariate data is R, such that R is very, very close to 0, then we say that the correlation between x and y is almost non-existent. Okay? Now, if R is closer to -1, or R is closer to 1, we say it is near positive, near perfect positive correlation, near perfect negative correlation. Finally, let's examine this fourth property. So let's put R on a real line such that we have 0, we have 1, and we have -1. Remember, R cannot exceed 1, it cannot go below -1. So let's put in between -1 and 0, let's put -0.5. In between 0 and 1, let's put 0.5. So please take note of this. If R is less than, if R is greater than 0, but very close to 0.5. If R is very close to 0.5, then we say that R tells us that the relationship between X and Y is weak, okay, but positive. So we would say it is positive but weak. When R is close to 0.5, greater than 0 but very close to 0.5. Now, if R is greater than 0.5 and very close to 1, we say R is positive and strong. So if you find your R, if your R lies between, your R value lies between 0.5 and 1, we say it is positive and strong. At 1, we say it is perfect, positive. If R lies between 0 and 0.5, less than 0.5, we say that R is positive but weak. Now let's come over here. If R finds itself between 0 and -0.5, we say it is negative and strong. It is negative and strong. But if R lies between 0.5 and -1, we say it is negative and weak. So please take note of these properties of the correlation coefficient because it will help you make inference when you solve any problem. Okay? So that being said, let's now look at what we call assumptions of a linear regression model. Please take note that linear regressions are fit based on the following assumptions: that number one, the relationship between X and Y must be linear, in this case for a bivariate data. Two, homoscedasticity holds, in the sense that the variances of the error terms are all equal. That is the case of constant or equal variance. Number three, multivariate normality, in which case the error terms follow a normal distribution with mean 0 and variance sigma square. We also have the properties like independence and lack of multicollinearity, in which case we assume that the variables are not correlated. Okay, so that being said, look at these properties. Let's now go over to solving a concrete problem. So now that we have learned all we've learned, let's now tackle a problem using what we've learned. The problem here on the board says, fit a linear regression model to the data below. Also obtain R using A, Pearson's correlation coefficient, B, Spearman's correlation coefficient. Now please take note, in this case, we are regressing Y on X. I repeat, we are regressing Y on X, in which case it will mean that Y is our dependent variable and X is our independent variable. So we are going to be fitting this model, Y on X, to this data. Let's do that quickly. So to fit our model, what we are going to do will be to rework that table. So I'm going to do this to the table we had drawn previously. I'm going to do this quickly. All you have to do is write your X, write your Y. I could call this Xi, Yi. Now, for what I'll be needing, I'm going to put the following. I know from the formula for beta 1 cap we obtained earlier on, there was xi squared. Okay, I'm also going to be needing yi squared. I'll put that. I'll also be needing xi times yi. I'm going to put that also. So this will help me get all I need. So I'm going to put this 1, 2, 3, 4, 5, and finally I'm going to leave this row for my totals. Okay, so now that you've done this, you can now put here 2, 4, 5, 9, and 3. For Y, we had 7, 6, 2, 8, and 6. Now, from the first column, you would notice you have xi squared. So whatsoever x is, square them. Okay? So 2 squared will give you 4. 4 squared will give you 16. 5 squared will give you 25. 9 squared will give you 81. 3 squared will give you 9. So I'm done with getting xi squared. I'm going to come over here. 7 squared will give me 49. 6 squared will give me 36. 2 squared will give me 4. 8 squared will give me 64. 6 squared will give me 36. Okay? Now, let's come over here and obtain summation xi, because we are going to be needing that to obtain the mean of xi. So what would we have there? 2 plus 4 plus 5 plus 9 plus 3. So this will give us 23. Now, for this summation from I equals 1 to n, yi, 7 plus 6 is 13, plus 2 is 15, plus 8 is 23, plus 6 is 29. So that should give us 29. Good. Now, coming over to this, so let's sum xi squared. But let's go to why we are actually doing what we are doing. Now, for beta 1 cap, please recall that the formula was n summation from I equals 1 to n, xi, yi, if you remember vividly, minus summation from I equals 1 to n, xi, times summation from I equals 1 to n, yi. All over, this would have been n summation from I equals 1 to n, xi, since we are regressing y on x, minus summation, this is xi all squared, hence the reason why we are computing xi, from I equals 1 to n, xi, close bracket, all squared. So, all we have put on the table comes from the formula. Okay? Now, let's go over to xi squared. So, let's add this. 6 plus 14 gives 20. 45. 45 plus 9 gives 54. 54 plus 1 gives 55 plus 80. That gives you what? 135. So I'm going to write here 135, and that will be summation xi squared from I equals 1 to n. Now coming over to the next one, from I equals 1 to n, we have 49 plus 36 plus 4 plus 64 plus 36. That gives 189. 189. So I'm going to hold on to that value. Then come over to xi, yi, because it's here in the formula. So let's multiply 2 times 7, the value of 2, the value of xi, which is 2, times the value of yi, which is 7, gives 14. 6 times 4 gives 24. 5 times 2 gives 10. 9 times 8 will give us 72. And 3 times 6 will give us 18. Okay? So let's add to get summation from I equals 1 to n, xi, yi. That will give us what? So you have 138. Now, someone can ask the question, why are we putting summation yi squared in our table when we don't have it in this formula? Please, this is just to solve the problem at once, because we have to find the correlation coefficient. Although yi squared does not appear in this formula, for the correlation coefficient, that is Pearson's correlation coefficient, it appears. So it is just to get everything done that we need at once. Now let's go over here. So in this case, what will our beta 1 cap be? Our beta 1 cap reduces to n, take note, is 1, 2, 3, 4, 5. You have 5 values under xi and yi. So n is 5. I'm going to put 5 here. Times, what is summation xi, yi? We got it to be 138. So this will be 5 times 138. Minus, what is summation xi? We added and we got it to be 23. What is summation yi? We added and got it to be 29. All over, what is n? 5 times summation xi squared, 135, minus summation xi all squared, which is 23 all squared. So now, let's now simplify. 5 times 138 will give you 690, minus 23 times 29, 667, all over 5 times 135, 675, minus 23 squared gives you what? 529. 529. So subtract 690 let's bring that result here. So I'm going to put it here. 690 minus 667 gives you what? 23. All over 675 minus 529 gives you what? 146. Now let's divide this. What would 23 divided by 146 give us? 23 divided by 146 will give us the exact value for beta 1 cap. Now what would that give us? 0.16 approximately to 2 decimal places. So this is our beta 1 cap. Now let's move over to getting beta naught cap. So now we have beta 1 cap to be 0.16 approximately. Let's obtain beta naught. For us to obtain beta naught, recall that yi is equal to y bar rather is equal to beta naught cap plus beta 1 cap x bar. Okay, now it means we need y bar. What is our y bar? It is the mean, and y bar will now be summation from I equals 1 to n yi all over n, and this gives us what's our summation yi? It is 29 divided by n, which is in this case 5. What would that give us? 29 divided by 5 gives us 5.8. Now, what's our x bar? Our x bar is summation from I equals 1 to n xi divided by n, which is 23 divided by 5. That gives us what? 4.6. So based on that, we can now proceed as follows. We can now write here y bar, which is 5.8, will be equal to beta naught, which we want to look, or simply we could just make beta naught our subject of formula, and that will be equal to what y bar is, which is 5.8, minus beta naught, which is 0.16, times x bar, which is 4.6. So let's see what that gives. 5.8 minus 0.16 times 4.6. What would that give us? 5.064. So beta naught cap will be approximately equal to 5.1 to 1 decimal place, or 5.06 to 2 decimal places. Okay. So now that we know these two values of beta 1 and beta naught cap, we can now say the fitted model. Therefore, the fitted model is, you write here y equals beta naught cap, which is 5.06, plus beta 1 cap xi, which is 0.16 xi. This will be the fitted model. This is the result we want. And with this fitted model, one can predict the value of y if one knows a value of x. Let's now move to the correlation coefficient quickly. So to obtain the correlation coefficient using Pearson's correlation coefficient, R, n summation I equals 1 to n xi yi minus summation from I equals 1 to n xi summation from I equals 1 to n yi was our numerator all over the square root of times the square root of. So this was n summation from I equals 1 to n xi squared minus summation I equals 1 to n xi all squared, n summation I equals 1 to n yi squared minus summation from I equals 1 to n yi all squared. Now, we put in our values in this case. This would give us our numerator. We had already computed our numerator, and we had 5 times summation xi yi, which is 138, minus summation xi, which was 23, times summation yi, which was 29. All over, let's drag this forward, all over the square root of n 5 times summation xi squared, which was 135, minus summation xi 23 all squared, square root 5 times for summation yi all squared 189, minus summation yi all squared, that is 29 all squared. So let's evaluate this to get our Pearson's correlation coefficient. So we would end up obtaining 23 for our numerator and square root of 146 times square root of 104 for our denominator. So Let's quickly divide. What would 23 divided by, in bracket, square root of 146 times square root of 104, close bracket, give you? 0.186, which is approximately 0.19 to 2 decimal places. So this certainly tells you that the correlation between x and y is weak but positive. It is positive because it is greater than 0. It is weak because it is less than 0.5. So that is the conclusion of that problem for Pearson's correlation. Let's now move over to end this problem with the rank correlation coefficient. Let's see. Now, when it comes to using the rank correlation coefficient, also known as Spearman's correlation coefficient, the first thing you do is to rank the values of x. Please take note that you rank the biggest number starting from 1. So 9 is the largest number here. I'm going to give it a rank of 1 because it takes the first position. I'm going to go over to 5, the next one, 2, 4 comes third, and 3 comes fourth, 2 comes fifth. Okay, so I have finished ranking x. Now, when it comes to ranking y, it's a little bit technical because of what is going to happen here. 8 ranks first, so I'm going to put it first. 7 ranks second. Now, you will notice that 6 and 6 occurs 2 times, so I'm going to give it a rank of 3. Ordinarily, this should be 4, so I'm going to put here 3, since both of them are the same. But since I rank this as 3 and 3, the next one automatically takes 5. And that is what I want you to know. Just because you've ranked these 3 and 3 does not mean the next should be 4. This one has taken 4. If there were 3 of them, it would have been 3, 3, 3, meaning that you will start the next number to them with 6. Okay? So that's how to rank when you have one number occurring more than once. So please take note of that. Now for the rank difference, I'm going to have DI, rank x minus rank y. Please, if you choose to rank y minus x, you still get the same result. So 5 minus 2 in this case is 3. 3 minus 3 is 0. 2 minus 5 is minus 2. And minus 3, sorry. And 1 minus 1 is 0. 4 minus 3 is 1. Now, let's square. 3 squared will give us 9. 0 squared comes 0. Minus 3 gives 9, all squared. 0 comes here. 1 squared is 1. So, I need summation di squared. And that will give me what? From 1 to 5. That will give me 18 plus 1, which is 19. So, that being said, I can now come over and say my formula is 1 minus summation 6 di squared from I equals 1 to 5 in this case, all over n in bracket n squared minus 1. Okay? So, this will be, let's put n there for now, rather. And you end up having 1 minus 6 summation di squared, which is times 19, all over n, which is 5, in bracket 5 squared minus 1. So my result ends up becoming 1 minus 6 times 19 gives me what? 114, all over 5 times 24, 120. So our result will be 1 minus, in bracket 114 divided by 120. What do we end up having? 0.05. Please verify these calculations or these computations at your leisure. And should there be any error, please let me know in the comment section. This tells you that your correlation is positive, okay, because it is greater than 0, but very weak because it is far less than 0.5. So that being said, thank you for joining my class on correlation and regression. I hope you learned something. Please watch this video over again and spot little errors wherever you can find them, if there are, and let me know in the comment section. Thank you very much. Until some other time.